My name is Erin Heffron, and today's webinar will be new tools for Watercolumn feature detection, extraction, and analysis. Our presenter today will be Mark Paton. He's our graphics and 3D interaction specialist at QPS. And on the panel, you'll have myself. My name is Erin Heffron. I'm the product specialist for Fledermaus. We also have Danny Neville, who's the Fledermaus product manager. And sitting in on this session, we also have Doug Burgeson of Acoustic Imaging, and he also runs the QPS Regional Support Center for Asia PAC.
Okay, there you. So, Erin, do you see my screen okay now? Can you hear me okay?
I see your screen and I hear you fine. Thanks.
Okay, thank you. Welcome. And I guess what I'm going to be talking about today is some basically recent work that we've been doing in both Midwater and Fledermaus to make it easier, more automatic, less arduous job to look at acoustic midwater data to be able to select, pull out features of interest and analyze that. And how can we basically streamline this entire process? And once we've got it streamlined, how much automation can we do? We've been, for quite some time now, we've been working with the Center of Coastal and Ocean Mapping at the University of New Hampshire. They have a team there, Dr. Tom Weber, his team, that have been investigating this problem. They've been developing algorithms and methods to examine midwater data and basically extract features of interest from it. And we've had for a while, I don't know how familiar everybody is with the Midwater tool, but there is a mechanism in place where you can extend it. Basically, have support for plugins where third parties can write their own algorithms, their own modules. We provide an SDK, a software development kit. They can use that to basically, without us having to do basically control it, they can create their own algorithms, try it out, see how it works. And we've also been collaborating with them for basically to move some of the most interesting of the algorithms that appear usable into core functionality of the software. And basically, work has evolved to the point with the latest release of 7.4.1. We've basically pushed forward some of these tools. We think for people who are interested in extracting contacts from midwater data, they're a big step forward from the process that was supported pre 7.4.1. So really, we want to go from something that looks similar to this, which is just showing a line of data, a series of pings from left to right, showing potential features of interest. You can see on the it's a bit subtle, but it's on the top left here. There's a couple of gas hydrate plumes. This is some data provided by NOAA, and this is some Kongsberg 302 data, I believe. And that's the data set that I'm going to be using for this example. In this particular thing, we're going to be talking about seep data, but it could potentially apply to any midwater contacts. So originally, this is what we have. We want to move to, this is the result we want to get to, where we've basically found these potential seeps. We've pulled out all the relevant contacts, basically look through all that noise and pull out the contacts related to the seeps, and then ideally characterize them, cluster them, characterize them, and say all these points on the far right here represent one seep, then this cluster over here represents another. That is our basic goal. There's actually, Erin will show this at the end, there's actually some very nice tutorials that she's put together and made available that show how to do the steps I'm going to talk about in detail again. So, I mean, you could argue the original way was show the midwater data and be able to select it and export it. The work we originally did with CCOM was to create a set of these plugins that basically did the steps. Everything in the Midwater tool is done by turning the sonar data into a generic Watercolumn file. It's sort of our internal Midwater supporting file. It goes through a process of normalization, which is just some statistical calculations. We actually make a second generic watercolumn file that's been, had this normalization process. And then if there looks like there might be some seep data of interest, there's another filter we call a despeckling filter, which attempts to basically get rid of the noise, leaving the seeps behind. If we can eliminate all that noise, it makes it a heck of a lot easier to export the data. This set of tools has been available for a while now, pre-741, and then there's really the new way, which is how do you make the process of exporting, finding and exporting the data, hopefully a lot faster, a lot easier, especially in areas where you have quite a large number of contacts. So the hopefully is we'll be able to launch a detection tool. Hopefully our filters will have good defaults, and we'll just be able to say, hey, look, there's the data. We can go grab it, export it, and do the cluster analysis. We may have to tweak the parameters a bit depending on the sonar type. Hopefully we can do that tweaking, and then again just export and go. And if that fails, you're sort of back to the old way. So what I'm going to do now, switch out of PowerPoint, run FMMidwater. I'm basically just going to walk through the process of a small data set for a single line. And I'm going to first do the series of steps where we have these tools, but we're not using the automatic tool. That's when we just say basically do the feature detection, but it'll give you the background for understanding where the tools come from. So if you're familiar with Midwater at all, like most of our Magic and other tools, you have to create a project. Most Midwater data is processed in geographic form. We're going to add some data to process. In this case, I'm going to add one line of this 302 data, both the bathymetry and the watercolumn files. When we bring this into the software suite, we basically just pull out the navigation. We can verify it looks like, okay, it looks like a decent navigation line. We haven't actually set up this generic watercolumn file, so that's always the next step. And if you had a lot of lines, you'd normally bring in all the lines at once and do them all in the step all in one. I'm just, let's say, doing the one line. Excuse me. I'm not going to go into detail of all the options. If you want me to come back and talk about them, that's fine. It's basically we're looking at where's the watercolumn data, where's the bathymetry data. We're not going to downsample it. We're going to select this is not dual head data anyways, but if it was dual head data, you'd have to choose which of the heads you want to process. You can only, in the Midwater tool, examine one head at a time. And now the system is basically going to run through all the raw data, build this internal generic watercolumn file that allows us to look at the pings. So basically, here's our time bar in the middle here, from 0 to 30 minutes, 35, 40 minutes. Starts at 25 minutes after the hour. You can also see the little picker on the left-hand side, just showing where we actually are in the line. One of the things we normally do, instead of just looking at this as a beam fan, we often turn this into a stacked view, which is just taking every one of those beam fans. This was the screen capture, showing it from basically left to right, collapsing those fans into a single line of pixels, and bringing the highest amplitude difference to the forefront. You can just see some of the hints of a few of the seeps right around the 32-minute mark or so. Another one over here, some faint indications of some other potential data. And before we had any of these tools, the only option for exporting the data would be to zoom in on this data, try and play with the various filters to get rid of some of the noise, and then use some of the tools to select and export. So move this thing out of the way here. But what I want to do is show not the most basic process, but using these plugins that have been created. So the way we would have used to have done it, let's go back to the fan view, was to take this generic Watercolumn file. We had a plugin that was produced originally from CCOM called basically Import Normalized GWC. We select that one I had, and it's basically going to ask me what kind of filter size do I want. This is going to say, 9 pings, basically 18 plus or minus 9 pings, and basically do a sliding window normalization process on the data. And it's just a first step in making it a little easier to pull out the individual, the features of interest. So now we have our normalized one. We can look at it as the stacked view as well. Just you can actually see that there's now some of the seeps which were hidden before stand out a little bit more. There's 2 over here to the left. There's 1, 2, 3, 4, at least 5 seeps down here. But that's not the end of the process. If I actually move, say, so the cursor's on one of these seeps and come back to the fan view, so you can see this is the one particular ping. There's another set of plugins available, which is the signal processing of the ping data, and one of these custom filter options that is the speckle, and this is a filter that attempts to to show the parameters. It has a series of parameters, whether it looks at 1 or 2 beams, how many the distance, the range of samples it will select, and it basically tries to find samples that have a significantly different amplitude, but that change in amplitude covers more than just 1 or 2 samples. You tighten up the percentages here, and this little the blue area will get smaller, and same if you play with the threshold. And really the goal, when it works well, as it does on this particular data set, it basically eliminates the vast majority of noise, leaving behind the data that we're interested in, and thus it makes it a lot easier to export. So this is what we used to do before 741. However, some of these operations are pretty computationally expensive. Jumping back and forth between the options still makes it a pretty significant effort if you wanted to do this for a series of lines. And this is where really the tool that I want to talk about now comes in, which is, I'll just go back to my original file. Assume I had not gone through the series of steps, as all I did was bring my data in, produce the generic Watercolumn file, and now we want to go into the, again, this is also a plugin that's been created. Oh, this is one that we've created based on the CCOM work. Run the Feature Detector. And this is a separate tool which is going to do essentially what I did, but in one step. When I select the file I'm interested in processing, click the synchronize button, and it will do the normalization process, do the despeckle process. It will use the default settings, but we can also customize those settings and then come back. I'll let this run for a second. Right now, this tool just shows the results in grayscale. It's something we want to bring the color map to it because it's a little easier to see. We just haven't quite done that yet. It's pretty hard to see the results in the normalization, but clearly in the despeckle process, you can see all the seeps standing out. You can basically click and drag, zoom in on the individual seeps, and there's a save tool here which will save any of the any of the data I've selected. A couple icons just to zoom back out, or back to the preview. It doesn't matter which view that you zoom into or zoom out of. It'll do both. This file has some noise and corruption at the back end of it, and these things down here are actually below the sea surface, or the sea floor. We'll go back, select the soundings, maybe tighten it up a little bit. Save these. It'll ask me for a file name. There are a couple options to do it. One of the most interesting I'm going to talk about in a minute is saving these points for doing cluster analysis in Fledermaus. You can also save it as a Fledermaus SD object, and the third option is a point object. There is a bug here where it adds .sd on the end of the file, which will confuse text editors, but it is a text file. You just have to change the file extension. That's something we'll fix in the patch. All the output is always, any of the outputs we do, we normally output to a projected coordinate system. It makes the analysis easier. It'll choose the default UTM zone nearest the center of the data that you have, which in this case is 15 north. You can change this to other ones if you so choose. And then it'll go through a process of taking all these individual points, and it'll also do a refraction process. Right now this tool is limited in scope to the Kongsberg sensors. We hope to add other sensors very shortly. In part, that's getting this refraction process to those other sensors. At this point, we've basically said these are all the features that we're interested in. We now want to move to Fledermaus to continue the analysis work. Up top here are just basically settings. There was the normalization settings. There's also an issue here that this is not properly being preserved. Again, that'll be fixed in the patch. And settings for the despeckle filter. The default settings here works great for 302 data, but the options definitely need to be tweaked if you start to get into, say, shallow water using that 2040 system or whatnot. There's a few other, the thresholds are a little bit different. The advantage of still having the older way to do it is sometimes you can interactively play and tweak with these settings, and then once you figure out your favorite settings, you can just put them in here, save them, and then run the process through line by line, and you're done. I'm just going to switch over. Aaron, was there any questions at this point?
Mostly we've been taking care of them, but this is actually a good question that just came in, and we'll give you an opportunity to clarify. We just got a question. Did you just say FMMidwater only works with Kongsberg data? So great time to clear that up and clarify exactly what you mean.
Sorry. No. The feature detection tool only works with the Kongsberg data, but Midwater works with many systems. So there's definitely, like, if you have a Reson or an R2 Sonics, that definitely works in the Midwater tool overall. It's just in the feature detection tool, and the main reason right now is the refraction correction. We may add an option just to say do a flat bottom assumption that would allow us to support other sensors faster, but we just have to talk to Danny and plan when that's going to happen.
Okay, and we just had one more question come in, and then I'll let you continue on. This might be something we have to address outside of our group, but I'll give you a chance at it. Would you be able to recommend some threshold settings for EM 2040 or 3002 data?
Not off the top of my head, but yes, we could for potentially for 2040 data. The main difference in the speckle tool was, let me just go to this fan. I'm just trying to do it by memory here. One of the biggest differences, this is deep water. This is about 1,300 meters. If you're using, say, a 2040, you're probably operating in much shallower water than that. And because that, you have a higher rate of pinging, and therefore it's you know, both the samples, and then you also tend to have more beams too. I tend to use like 3. Basically, increase the spread of looking for differences, increase the number of samples, pretty much increase the spectra rate, and increase the threshold. I think I used 7, but you know, I can't say for the 3002 without seeing a sample. Big thing is play with it in, you know, the old process first, where you can go in the signal, you can just see as you adjust the options, you know, you can interactively see if they help or not. If you get a good set of options, then run the tool and batch it. And there was questions in the early webinar which asked about, you know, can you batch process lines of data? And you can only process one GWC file at a time, but you can load multiple lines and concatenate them into a single GWC file. Although if it starts to get a really long, really long line, you could potentially run into problems. Hopefully, you know, in the future we'd be able to just say, you know, if you have 10 GWC files, just run it for all 10 and export it 1, 2, 3. But that's where we're at now.
Okay, thanks, Mark. That's all the questions in right now, so you can continue. Thank you.
So I had just set up a little bit of a scene already, just so it would save a bit of time. This is the same data set with those exported points. Just to put a basic surface in, I had used the, you know, import on grid data, selected that .all file, and produced a 10-meter surface. So I had sort of a basis for seeing my points, and these are the ones that the feature detection tool exported. You know, this is where it helps to be able to look at them from all angles. You can clearly see there's basically a series of seeps in this area. Some noise, points as noise right now. I actually go to my contacts. You're familiar with Fledermaus point objects. That's essentially what it is. All the same set of attributes. Make the points smaller or big. They're color coded by, in this case by default, they're color coded by amplitude. You know, if we just changed it to height, you know, colored by height. I'm just going to go back to amplitude for a second. You can see in the data the actual series of items that are stored for every exported contact. Basically, it's X, Y, and Z position. It's amplitude, the time it was recorded at, what beam it came from. These extra 4 fields at the end, the cluster ID, number of points, accepted, characterization, are basically fields that we're going to use in a second when we start and basically run a process where we can say, look for points that have a good proximity with another set of points and group them together into meaningful clusters of points. And I'll come back to these in a sec. So the tools here, the same as the point object. The biggest difference is the series of the actual menu options you have under the tools menu. And the key one is running the clustering algorithm. And basically it has 2 key parameters, which is basically the planar XY planar distance, minimum distance required between 2 points, and the same for Z. The reason why we chose to separate out into the 2 planes is because it makes it easier to look for clusters that have a certain shape. In this case, seeps often tend to be, you know, tall, structural. Sometimes they bend over. because the hydrates are moved by the currents. But it allows you basically finer control over how the clustering works. The way the algorithm processes the data, it basically just starts with the first point it has, and there's about 5,000 points here. It starts with the first point. It basically says, is there another point within the two distances that satisfies both criteria? If there is, it becomes part of the associated with the first point, and that's the first cluster. It then says, okay, what about that point? Are there any other points that are within the satisfies the criteria again? And it goes. It tries to maximize the number of points it can find, so maximize the size of the clusters. When no more points meet the criteria, it looks for the next unclustered point and repeats the process again. So and you can run this as many times as you want with different parameters. For example, if we leave the XY distance, but let's change it. This is deep water here, so 20 meters and 130 are not that far. I'll talk about the minimum seep size in a second and say okay. I haven't changed the color by, so it doesn't look like it did anything. If we actually look at the table now, we'll see that there's a cluster ID, how many points contained within that cluster, was it considered accepted, and we'll see characterization is something we don't use yet. We want to use more for attempting to automatically analyze or guess at what the set of features might be. At the moment it's not used. The accepted field is actually that parameter you saw here, which is the minimum size. How many, if the cluster has at least 100 points, it's just marked as accepted. In other words, in this case, a likely seep. So I'll change the color by instead of amplitude. Let's go to cluster ID, and you can see that the color map range here changed from 0 to 48. So basically saying we have 49 different clusters in the calculation. And it's just using those 49 positions mapped into the color map to assign the colors. One of the sort of useful other tools is to create. You can step through the data and look at all the individual points, but it's a little easier to create this cluster summary of object, which if you do, it actually creates another normal point object. I'll just make the size bigger so you can see it. Let's actually change it to a diamond and make it bigger so we see. So if you see all in the scene now, basically the cluster summary will place a diamond at the lowest point of every cluster. And the reason why we just use the lowest point is it at least for seeps, it's likely to represent the closest point of the surface where the seep is coming from. So if we drape these points on the surface, it'll show us basically the likely XY source of the XY and Z source of the cluster. I'll make it smaller. You can actually see there's a cluster with 1 point because none of the other criteria was met. And we can clearly see that there, in this case here, I was a little bit fine in on my choices of the ranges. If I give it a little bit more, probably in X and Y, and maybe a little bit more in Z, it'll likely group these. We intuitively looking at these, we know this is basically this vertical bar. These vertical bars are individual seeps. So I'm just going to go back, run it again, increase my XY distance a lot, and maybe go to 170. Most of these distances are going to be based on depth. If you were shallow water, you would have much smaller numbers. You'd have more samples likely of interest. So now you can see that the range of the color map went from, before it had 49, 0 to 48, now it has 0 to 16, so 17 clusters processed. If I do that, create a new summary, And again, change it to diamond so we can see it a little bit better. And so now you can see most of the clusters, except for a bit of noise, are now properly identified the seeps, and they're at the bottom of the seeps. And the nice thing about the summary is it just, now you only have one entry which contains, the original cluster ID, the total number of points, whether it met that 100 criteria that I had or not. There's a little tool here, you can use a flag, and if you do that, it puts a vertical, you can see that, but basically a vertical red bar through the cluster that I have selected. This feature should also work on the actual cluster object as well. There is a bug there. It's not locating the individual points. We'll have to solve that, but it certainly works on the cluster summary. And then, any of the standard export options for points, if you want to just export them to a file, are available. The full cluster object itself has several additional exports. Basically, creating the export cluster information will basically write a text file. If you look at the links Aaron shows, it'll give some examples of what it looks like, but it basically say, cluster 0 has this many points. Here's the series of points, cluster 1, and so on. And if you want to get just a dump of this data to an Ascii file, you could do it here, although you could have done it from the seep hunter itself as well. Sorry, whoops, I didn't mean to do that. And it's the same options that a point has for exporting this to ARC. If you're an Esri user, that's available too. I color by number of points. Is there any particular questions that have come up?
Hey Mark, I do have one question. It kind of takes us back to the processing a little bit. We understand that the seep detection tool itself works for Consberg data, but as far as the older options with the speckle filter and doing the normalization on the GWC kind of more manually, do those options work on SegY? And if they do you have any experience with it? Does it work well?
I think they will. I've never personally tried it, so I couldn't answer the question if they would work well. If somebody wants to provide us with some data, we'd be happy to. Be happy to try it. In theory, it should work. I've just not personally. I don't know anyone who's actually tried it.
Okay, great. You have a volunteer. So
that's basically the. Okay, that's great. Yeah, it'd be great to get. I'd say more examples we can get, the better, because that helps us verify the functionality. That's basically the set of tools that I wanted to talk about. Just come back here for one slide and talk just a little bit about what's in the we've already been talking about in the immediate future. Basically, the batch processing of multiple lines, and it is important to us to continue to support more and more sensors and get data in different environments, sensor environments I'm talking about. And then within Fledermaus, the cluster object itself is just actually some more editing and cleaning, like just saying an option to dump and get rid of all the clusters that, for example, weren't accepted. Just a couple of tools to make that easy. You definitely see it would be nice to be able to sometimes merge clusters. Where you see two, they're clearly clusters, but you could visually say, hey, these are the same, without necessarily having to try and tweak the parameters. And of course, we want to look more at the characterization process. I mean, seeps tend to have a certain shape, so there's the potential for some automatic characterization. If there's possible wreck structures on the seafloor, can you potentially differentiate from fish schools versus versus noise and so on? And this whole process, the only way with 741 to actually get a clustering object is to use that feature detection tool right now in Midwater. We definitely want to make it so anybody can just import generic, if you have an Ascii point file that was exported from another system, we want you to be able to bring it in and to use it in Fledermaus and do this kind of analysis. So those are some very obvious things that are in the forefront to do, hopefully sooner rather than later.
Hey Mark, I did have another question come in. The feature contacts seem to be focused on seeps. How does it handle large detections? Have you tried it on wrecks or other underwater structures?
Not a lot. Most of the sample data that we've had has been seeps. I would expect it to work pretty well if you had clear, basically anything that has a clear contact. I know it works with some structure. Like if we've seen construction and stuff like that exists on the seafloor, it can certainly detect that. Same process works fine, because really what it's looking for is there's a lot of noise, but the noise tends to be signal no signal, signal no signal. It tends to vary very rapidly. So it's the whole despeckling and normalization and despeckling is about being able to see where there is some consistency in the signal, highlighting that and eliminating the rest. So I'd expect it to work pretty well, but again, somebody wants to provide us with data, we'd be happy to try it.
Okay, thanks Mark. If you're all set then, I'll switch the presenter back to me. If anybody else has questions, keep them coming in. If I don't see them come in, because I'll be talking now, we will get back to you later. So don't worry, I will be following up after the webinar. But just to follow up, I'd just like to go back to my slides and just show you the links to a couple of resources and where you can find them. So if you can bear with me for a moment. All right, so hopefully you're seeing my screen again. Let me get my presentation back up.
Yep, you are.
You can see me? Okay, great. All right, so just in review, these were the resources Mark had mentioned. So this webinar itself has been recorded and will be a resource for you. I do post the recordings, for the newer webinars to the website. We also maintain download links. So in a couple of days at most, it will be up on the website. And if you'd prefer to download it so that you can view it offshore or whatever, you can just email me or the webinars at qps.nl email, and we'll provide you with those download links. That's not a problem. Other resources, we have, as Mark mentioned, 2 how-tos, which I'll be updating as we get more stuff documented. But they kind of give you a good start on how to use these tools. We have one for the feature detection and one for the point cluster SD object. I realize you're not going to follow these links or write them down. The presentation will be available if you ask for the download, but I'm also going to, in a moment, go to the website and show you how to get to these 2 locations. But before that I do that, the one other thing I wanted to mention, the 741 came out a few weeks ago, and we've been playing with this, and the tool's gotten out. So there are 2 known issues that we do know about at this point, and Mark mentioned both of them during the presentation. If you make changes to the normalization settings, and that's within that feature detection tool itself, if you change the filter size, it's not being honored. So it's not remembering it, it's not using it, and we do realize that that's an issue, and it will be fixed soon. And the other one was the Ascii dump export from the point cluster. So when you went to save in the feature detection tool, if you chose to do the Ascii dump, it's saving it with an SD extension. It actually is a text file, it just has the extension SD, and if you try to open it in Fledermaus, it won't work. You can force a text editor to open it. You have to change the extension and play with it a bit. So these are two issues we do realize are there and have been reported and documented, and we're working on getting those fixed. And of course, if you ever have any issues, don't worry about repeating things. Please just let us know. I'd rather hear it twice than not know about it. All right, so that's that. And if you just give me a moment, I'd like to take a second to show you where you can find those resources on our website. I know that the website can sometimes not be very easy to navigate around, so I'd just like to point you to those resources. So the QPS website, www.qps.nl, and we put most of our technical stuff under support. So I'll go there up to support. All right, and this is where I had the images in the presentation. This is where you can contact support or learn about our support ticket system. But what I'm trying to get to now is more technical information. And there's repeats, so some of these links might take you to the same places, but these are the ones I know about, so I'm going to go through here. So I'm going to go to the Fledermaus knowledge base. And under that, you have recorded webinars. So once this webinar is ready to go, it will be listed here for viewing. You can't download from that location, but you can view it from the website. If you want the download, again, just let me know. Email me and I will send you the link. And then the other resource is under Fledermaus resources, we have how-tos. And so this is something we're working on building up, trying to get more basic how-to information for the Fledermaus Suite. And the two that were created for this tool, this set of tools specifically, is how to use feature detection in FMMidwater. So you have your step-by-step on using that tool. And then the other one has to do with the point cluster SD. So how to perform cluster analysis using the point clusters. All right, and again, if I get that up, page by or step-by-step directions with images. All right, so just a couple of resources to get you started. Thank you again, everyone, for attending our webinar. We hope to see you on future webinars. We have a few in the works, thinking backscatter in the next couple of months. For anyone who put in requests when you registered for this webinar, I do appreciate it, and I do read that, and we try to get things scheduled that people ask for. So thanks for taking the time to do that. Thank you, Mark. Thanks, Danny.
Thank you all for listening.
Yeah, and thanks, Doug, too, for coming and sitting on and being a panelist. And again, thank you all, and the webinar should be up in the next couple of days. Have a good night.